Welcome to my channel, which is about science explorations and mysteries. I'm so glad you're here. Tonight, as you lie back and let the day slowly dissolve, we're going to wander through 100 mysteries that science still hasn't solved, from the birth of the universe to the way your own mind works. We'll drift gently through questions that don't yet have answers, questions that make reality feel deeper, stranger, and more beautiful than we usually remember. You don't need to solve anything. You don't need to understand every detail. All you have to do is listen, breathe, and let these mysteries wash over you like waves in the dark. If you feel like returning to this world of questions again, you can always come back. But for now, if you're ready, let's begin. And if you'd like to uncover more mysterious things, don't forget to subscribe. No one knows why the universe exists in the first place. We can describe how it behaves, how galaxies move, and how atoms interact. But the most basic question, why is there something rather than nothing, is still completely unsolved. Physics can trace events back to the Big Bang. Quantum theory suggests that even empty space is bubbling with virtual particles. Some imagine a multiverse where countless universes blossom with different laws, but that only pushes the question back. Why is there anything at all, rather than an endless silence? The fact that reality is here at all is the first and deepest mystery, a question so enormous that every other question rests on top of it. We also don't know what actually triggered the Big Bang. We can roll the clock back almost 14 billion years, see the universe as a hot, dense fireball, and watch it expand and cool. We can even guess that something like inflation, a burst of unbelievably rapid expansion, happened in the first fraction of a second. But what sparked it? What made nothing explode into everything? Was it a quantum fluctuation, a tremor in the fabric of reality? Was it one bounce in an endless cycle of collapsing and reborn universes? Or did time itself begin there, making the question, what came before, meaningless? The first moment stays hidden behind a curtain we can't yet pull back. Time, for us, only flows one way, and no one can explain why. You remember yesterday, not tomorrow. A dropped glass shatters, but never leaps back together. Heat leaves your coffee and slips into the room, but never crowds back into the cup. This one-way direction is called the arrow of time. And yet, the fundamental laws of physics, written down in equations, don't demand an arrow at all. They work perfectly well, forwards or backwards. Many scientists connect time's arrow to entropy, the tendency for disorder to increase. But then we hit a new puzzle. Why did the universe begin in such a strangely ordered low entropy state? Time's flow is the stage on which your whole life takes place, and we still don't know why it runs forward and never in reverse. Most of the stuff in the universe is invisible, and we don't know what it is. When astronomers watch galaxies spin, they see something impossible. Stars at the edges are moving too fast, as if held by an unseen hand. Gravity from visible matter isn't enough to keep them bound, yet there they are, circling steadily. The simplest explanation is that there's extra mass we cannot see. Dark matter. It doesn't glow, doesn't reflect, doesn't block light. We only know it's there because of its gravity. It shapes galaxies, bends the paths of distant starlight, and helps weave the cosmic web itself. But is it made of unknown particles, primordial black holes? Something stranger we haven't imagined yet? After decades of searching, every detector is still waiting for a clear ping. For now, dark matter is a ghost that holds the universe together. And then there's an even more mysterious ingredient: dark energy. In the late 1990s, astronomers expected that the universe's expansion was slowing down, tugged by gravity. Instead, they found the opposite. Space is expanding faster and faster, as if pushed apart by something hidden in the very fabric of the void. This dark energy seems to make up about 70% of everything that exists, yet we have no idea what it really is. Maybe it's a constant energy of empty space. Maybe it hints at new physics or a cosmic field that changes over time. Whatever it is, it's steering the fate of the universe. Will everything fade into cold emptiness? Will space tear itself apart? The answer is tied to a force we can measure but not understand. The laws of physics seem suspiciously fine-tuned for life. If gravity were a bit stronger, stars might collapse too quickly. If it were weaker, galaxies might never form. Slight changes in the strength of the electromagnetic or nuclear forces could prevent atoms from forming or stars from burning steadily. It looks as though the universe sits on a knife's edge. Tiny tweaks to the fundamental constants, and life becomes impossible. Is this an incredible coincidence? Is there a multiverse of many universes, and we just happen to live in the rare one that works? Or is there some deep principle that forces the numbers to be just so? No one knows, but every breath you take depends on a cosmic balance we cannot yet explain. We don't even know how big the universe truly is. The part we can see, the observable universe, is enormous, about 90 billion light years across, but light has only had so much time to travel. Beyond that glowing shell of visibility, reality continues. It might stretch on forever. It might curve back on itself like the surface of a sphere. It might be patchy and strange in ways we can't observe. We search for clues in the faint afterglow of the Big Bang, in patterns in the cosmic microwave background. So far, the data suggest a universe that is very nearly flat, but flat doesn't necessarily mean infinite. We live inside a bubble of light, surrounded by regions that will forever remain out of reach, no matter how long we wait. Some scientists even suspect there may be other universes entirely. The multiverse idea sounds like science fiction, but it slips naturally out of several theories. Inflation might create bubbles of reality that blossom and pinch off, each with its own properties. String theory suggests a vast landscape of possible universes with different laws and constants. In this picture, our universe is just one island in an unimaginably large archipelago of realities. It could even explain fine-tuning. We find ourselves in a universe that allows life because in the universes that don't, there's no one there to ask the question. The hook, of course, is that we may never be able to test this. If other universes exist beyond our cosmic horizon, no light, no signal, no probe will ever reach them. The multiverse sits at the edge of science and philosophy, both thrilling and frustrating. Space and time themselves might not be fundamental. Einstein taught us that space and time are not rigid backgrounds, but flexible, bendable, stretchable. Massive objects warp space-time, guiding the paths of planets and light. But when we zoom in to the tiniest scales, this smooth fabric clashes violently with quantum mechanics, which insists that everything is jittery, grainy, and uncertain. Some physicists now suspect that space-time is not basic at all, but emerges from something deeper, perhaps networks of quantum information, patterns of entanglement, or structures we don't yet have words for. If that's true, then here and now are not the foundation of reality, but the surface of something more fundamental. We live on the stage, not in the backstage machinery that built the stage. On the quantum level, a single particle can be in many places at once, and no one really understands how. Quantum mechanics says that until we measure it, a particle doesn't have a definite position. Instead, it exists in a cloud of possibilities called a superposition. In experiments, electrons can pass through two slits at the same time and interfere with themselves, behaving like waves. Molecules far larger than atoms can be put into this ghostly both-at-once state. Yet, whenever we look closely, whenever we measure, we always see a definite result. Here, not there. Does the world split into multiple branches, each realizing a different outcome? Does the act of measurement physically change reality? Is superposition a real physical thing, or just a tool for calculating probabilities? Quantum theory works brilliantly, but its meaning is still a riddle. Entangled particles share a connection that seems to ignore distance. When two particles become entangled, measuring one instantly tells you something about the other, even if they are separated by light years. No signal travels between them as far as we can tell, and yet their results are perfectly correlated, as though reality itself is keeping a hidden ledger. Einstein called it spooky action at a distance. Experiments keep confirming that the world really does behave this way. Some physicists think this means reality is deeply non-local, that space and time are not the fundamental stage we imagine. Others think there may be hidden variables we haven't uncovered yet, or that information has a deeper role than matter and energy. Whatever the explanation, entanglement suggests that the universe is stitched together in a way our everyday intuition simply doesn't capture. Even stranger, observing something seems to change what it is. In the famous double-slit experiment, particles act like waves and create interference patterns until we try to detect which slit they pass through. The moment we measure their path, the wave-like pattern disappears and they behave like little bullets. Why should the mere act of obtaining information change the outcome? We describe this with the collapse of the wave function, but that phrase is more of a label than a true explanation. Does consciousness matter? Are measuring devices special, or is everything just following deeper rules that we don't yet know how to write down? The universe, at the quantum level, seems to care about what can be known, and we don't know why. Gravity, the force that shapes the cosmos, is weirdly weak, and no one knows why. Lift a paperclip with a small magnet, and you just defeated the gravitational pull of an entire planet. The strong and weak nuclear forces, electromagnetism, on tiny scales, they're all far more intense than gravity. Physicists call this the hierarchy problem. Why is gravity so feeble compared to the others? Maybe it leaks into extra dimensions that we can't see. Maybe the true strength of gravity is hidden behind physics we haven't discovered yet. This imbalance isn't just a curiosity. It determines how stars form, how planets orbit, and even whether complex structures like galaxies and you can exist. Our two best theories, quantum mechanics and general relativity, both work incredibly well, and yet they refuse to fit together. General relativity describes the large-scale universe, planets, stars, black holes, and expanding space. Quantum mechanics describes the small-scale world. Atoms, particles, fields, forces. Each has passed every test we've thrown at it, but in places where we need both, like inside a black hole or at the very beginning of the universe, our equations explode into infinities. We get nonsense instead of answers. Many scientists search for a single theory of everything that unites them: string theory, loop quantum gravity, and other candidates make bold promises. So far, none have been confirmed. The universe is telling us that there is a deeper framework where both quantum rules and gravity make sense together. We just haven't found it yet. The hearts of black holes are still hidden from us. We know black holes exist. We can see stars orbiting invisible objects. We've imaged the glowing rings of matter swirling around them. But what lies at their center? According to Einstein's equations, everything falls inward to a singularity, a point of infinite density and zero volume. Infinity is usually a sign that a theory has reached its limit. Does something else happen instead? Is the core a tangle of quantum space-time loops? A region where our usual ideas of space and time simply fail. We can't look inside. The event horizon keeps the truth forever out of view. Somewhere beyond that one-way boundary, the laws we know give way to something we've never seen. Even the nature of singularities themselves is a puzzle. They appear in black holes, and possibly at the beginning of the universe. Our equations say, here, everything breaks down. Are singularities real physical things? Or are they just warning labels telling us, don't trust this math here? Many physicists suspect that a future theory of quantum gravity will smooth out these infinities, turning impossible points into something finite and comprehensible. But until that theory is found, singularities sit like holes in our map of reality, places where our understanding drops to zero. We're not even sure what happens to information when it falls into a black hole. Throw a book into a fire, and, in principle, the information it contained is scrambled but not lost. In theory, it's still encoded in the smoke and heat. Physics depends on the idea that information is conserved, but tossing something into a black hole is different. If the black hole eventually evaporates through Hawking radiation, where did the information go? Did it vanish, breaking the rules of quantum mechanics? Is it somehow encoded in the radiation in a way we don't understand? Does it survive on the event horizon like a hologram? This black hole information paradox has been argued over for decades, and although there are promising ideas, no consensus has emerged. It's not just about black holes. It's about whether reality can truly forget. Hawking radiation itself is still a prediction we've never directly seen. Quantum theory says black holes shouldn't be perfectly black. They should leak a faint glow, slowly losing mass over unimaginable spans of time. Tiny black holes would evaporate faster. Giant ones take longer than the age of the universe. The math is elegant and connects gravity, quantum physics, and thermodynamics, but we've never detected Hawking radiation from an actual black hole. The universe is too noisy, the signal too weak. Lab experiments have created analog systems like fluids and sound waves where something similar appears to happen, but whether real black holes truly evaporate is still an open question. If Hawking was right, black holes are temporary. If he wasn't, then something even stranger is lurking in our theories. Some scientists even wonder if black holes could lead somewhere. Certain solutions of Einstein's equations hint at wormholes, tunnels linking different regions of space-time, or even different universes. Could a black hole be an entrance to such a passage? Probably not in any safe way. The forces near the center would shred almost anything. And yet, the math doesn't rule out the possibility of exotic structures where what falls in might contribute to new regions of space-time. Are black holes cosmic trash compactors or cosmic seeds? Right now, they are locked boxes we cannot open. The possibility that they're more than just dead ends is one of the most tantalizing hooks in modern physics. We still haven't seen the very first stars that ever shone. After the Big Bang, the universe cooled, darkened, and filled with hydrogen and helium. At some point, those clouds collapsed under gravity and ignited the first stars, huge blazing giants made only of primordial elements. They lit up the cosmos and forged the first heavy atoms in their hearts and explosions. We call them population 3 stars, but no telescope has caught one directly. They were massive and short-lived, dying long ago. We look for their fingerprints in the chemistry of ancient stars, in the faint glow of far-off galaxies, in clues buried deep in cosmic light. But the exact story of how the universe switched on its first beacons is still incomplete. Some black holes in the early universe are far too big, far too soon. When we look back billions of years, we find supermassive black holes already sitting at the centers of young galaxies. They're millions or billions of times the mass of the sun, and they appear when the universe was still a child. How did they grow so fast? Did they form from the collapse of gigantic gas clouds, skipping the usual star stage? Did unusually large first-generation stars leave behind oversized black hole seeds? Or are we missing a growth mechanism that lets them gorge themselves more quickly than our current models allow? These ancient giants challenge our understanding of how galaxies form and evolve. Even the graceful spirals of many galaxies are still not fully understood. The Milky Way, our home, is one. So are many of the galaxies we see in images, delicate arms curling outwards, full of stars and gas. Why do these spiral patterns form and persist? One idea is that they are density waves, like traffic jams that stars move through. Another suggests gravitational nudges from nearby galaxies sculpt them. Simulations can produce spirals, but the full story, the stability, variety, and long-term behavior of these structures isn't perfectly settled. When you look up at that hazy band across the sky, you're looking from inside a mystery we still haven't completely solved. Across the universe, sudden radio flashes shout at us, and we don't know what's yelling. They're called fast radio bursts, FRBs, and they last only milliseconds. Yet, in that blink, each one can release as much energy as the sun does in a year. Some repeat, others flare once and never again. Candidates include magnetars, collapsing stars, or collisions of compact objects. But no explanation fits every burst. We've traced some to distant galaxies. We can line up their signals, count them, analyze their spectra, but every time we think we're close to a complete answer, another weird burst appears that doesn't fit the pattern. Pulsars, spinning corpses of stars, keep time with eerie precision we still can't fully explain. They're neutron stars, city-sized balls of ultra-dense matter, spinning rapidly and blasting beams of radiation into space. As they rotate, those beams sweep past us like cosmic lighthouses, ticking with incredible regularity. Some pulsars are more stable than our best atomic clocks, and yet they occasionally glitch, changing speed abruptly in ways we don't fully understand, perhaps due to exotic superfluid interiors. These objects are laboratories of physics far beyond what we can recreate on Earth, and they continue to surprise us. Magnetars go one step further, exploding with unimaginable magnetic tantrums. Magnetars are neutron stars with absurdly strong magnetic fields, up to 1,000 times stronger than ordinary neutron stars and trillions of times stronger than Earth's. Sometimes those fields twist and snap, releasing flares of X-rays and gamma rays powerful enough to disturb Earth's upper atmosphere from across the galaxy. Are these eruptions driven by starquakes in a crystalline crust, sudden rearrangements of magnetic fields? Something we haven't yet imagined. Their violence hints at physics that we only barely understand. High-energy cosmic rays crash into our atmosphere with energies we can't easily explain. Most cosmic rays come from known sources: the sun, supernovae, and energetic events in the galaxy. But some arrive with energy so extreme that we aren't sure what could have launched them. They carry the punch of a fast baseball packed into a single subatomic particle. They curve through galactic magnetic fields, hiding their true origin. Are they coming from supermassive black holes, the decay of exotic particles, regions of space where physics behaves differently? We build giant detectors across deserts and ice fields to catch their cascades, chasing hints of something powerful and mysterious beyond our view. Even the emptiest parts of the universe, cosmic voids, raise questions. Galaxies aren't scattered evenly. They form threads and clusters, leaving vast regions almost empty, cosmic voids that can span hundreds of millions of light years. Simulations show that gravity naturally pulls matter into filaments, leaving emptiness between. But some of the largest voids seem bigger and stranger than expected. Do they hint at new physics in the way structures form, or are they just rare but possible outcomes of cosmic chance? These enormous holes in the universe test our understanding of how matter clumps and how space expands. We don't know how the universe will end. Will it expand forever? Stars slowly burning out, galaxies drifting apart into the cold black silence of heat death. Will gravity one day reverse the expansion, pulling everything back together into a big crunch? Could dark energy grow stronger and stronger, tearing galaxies, then stars, then atoms apart in a big rip? The answer depends on the true nature of dark energy and the exact balance of matter and energy in the cosmos. We have clues, but not certainty. The universe has a beginning we partially understand. Its ending is still a question mark. Something started cosmic inflation, and we don't yet know what. To explain why the universe looks so smooth on large scales and why its temperature is so uniform, inflation proposes that in a tiny sliver of a second, space expanded faster than the speed of light. The idea fits the data remarkably well, but what field drove that expansion? How did it start? Why did it stop? The inflaton is a hypothetical field that has never been directly detected. Inflation might be exactly right, or only an approximation of something even stranger that preceded the Big Bang as we describe it. Now we turn toward a different mystery: life. We don't know how life first began on Earth. We know that by about 3-5 billion years ago, microbes already existed. But how did lifeless chemistry transform into the first cell? Did life start in deep-sea hydrothermal vents, where hot water and minerals create rich chemical gradients? Did it arise in warm, shallow pools on land, where evaporation and refilling could concentrate molecules and drive reactions? Did key ingredients arrive from space on comets and meteorites? We've made amino acids and other building blocks in the lab, recreating early Earth conditions, but assembling a self-sustaining, evolving system from scratch is a leap we still haven't bridged. We're not sure whether life began in the ocean, on land, or in some combination. The deep ocean offers stability and energy, but also dilution. Land pools offer concentration and cycles of wet and dry, but also instability. Both environments could have hosted the first spark. The evidence has been eroded, melted, and transformed by billions of years of geology. We are left with hints in ancient rocks, subtle chemical traces, and bold, competing models. We don't know exactly how the first true cells formed. Modern cells are astonishingly complex: membranes, molecular machines, DNA, RNA, proteins. One idea is that simple fatty molecules formed bubbles, naturally creating compartments. Inside these little vesicles, chemistry could proceed, protected from the outside world. Gradually, some compartments might have evolved ways to copy information and harvest energy, crossing the line into real life. We can see primitive versions of this in the lab, lipid bubbles that form spontaneously and enclose molecules. But the step-by-step path from that to the first living cell is still missing. DNA's double helix seems like the perfect storage device for life's information, but we don't know why nature chose it. In principle, there could be many ways to store information chemically. Early life may have used RNA as both a catalyst and a memory keeper. At some point, DNA took over as the main archive. It's stable, efficient, and elegant. But was this inevitable, dictated by the laws of chemistry? Or was it an evolutionary accident that just happened to work extremely well? Every organism you know depends on this twisting ladder of nucleotides, yet we don't fully understand why this structure became universal. Viruses blur the line between life and non-life, and their origin is an open question. They can't reproduce on their own. They hijack living cells, turning them into virus factories. Some scientists think viruses are leftovers from an ancient RNA world, fragments that survived by parasitizing cells. Others believe they started as bits of genetic material that escaped from cells and became independent. Still others think they evolved from once free-living organisms that shed unnecessary parts until all that remained was a husk, carrying just enough instructions to invade. However they began, viruses are ancient and powerful, and they've shaped evolution in ways we're only beginning to understand. On early Earth, countless molecules formed, but only a few crossed the threshold into life, and we don't know what made them special. Lightning, volcanic gases, sunlight, and mineral surfaces all encouraged rich chemistry. Many different organic compounds would have formed. Why did certain combinations begin to self-replicate, adapt, and evolve, while others stayed inert? Was life an almost inevitable outcome when conditions were right, or an extraordinary fluke that might never repeat exactly the same way again? The answer decides how likely life is elsewhere in the universe, and at the moment, we simply don't know. We don't yet know whether life exists anywhere else. We've found thousands of planets around other stars, many in zones where liquid water could exist. We've discovered organic molecules in interstellar clouds, on comets, and on icy moons. Mars shows signs of a wetter, warmer past. Europa and Enceladus hide oceans beneath ice. The ingredients seem widespread, And yet, no confirmed microbe, no fossil, no unmistakable alien signature has appeared. The universe is vast, and our search so far is tiny. Are we one of many, or utterly alone? That silence, so loud in its emptiness, is one of the most haunting questions we face. We don't know whether life must look like us at all. Every living thing we know uses carbon, water, DNA, or RNA, and similar biochemistry, but that's based on a sample size of exactly one planet. Could there be silicon-based life or organisms that use ammonia instead of water? Could something we'd never recognize as alive, patterns in plasma or self-organizing magnetic structures, qualify as a different form of life? Our definitions are shaped by what we've seen. The universe might be far more imaginative than we are. We're unsure how many truly habitable worlds are out there. It's not enough for a planet to be at the right distance from its star. It needs long-term stability, the right atmosphere, protection from deadly radiation, and probably liquid water somewhere. Moons might be habitable too, with subsurface oceans warmed by tidal forces. The galaxy could be littered with Earth-like havens, or they could be astonishingly rare. Every new exoplanet we discover is another clue, but the full picture hasn't come into focus yet. And so, the oldest question stays open. Are we alone? We've listened for radio signals, we've searched for technosignatures, we've probed Mars, scanned icy moons, and studied exoplanet atmospheres. So far, nothing definitive. Maybe intelligent life is common, but too far away. Maybe civilizations burn out quickly, maybe life itself is rare, or maybe our methods of looking are still too limited. Every quiet sky is a hook that keeps us wondering. Now, we turn inward to the most personal mysteries of all, the mind. Consciousness arises from the brain, but we don't know how. Electrical impulses flicker along neurons. Networks light up when you see, think, or remember. We can track brain activity when you recognize a face or feel pain. But none of this explains why there is a feel to any of it, why there is an inner world at all. A brain is a lump of matter. How does it produce the bright private experience of being you? Some theories link consciousness to particular patterns of information, others to integrated networks, others to fundamental properties of reality. But so far, the gap between firing neurons and the taste of chocolate, the color red, the ache of loneliness remains wide. Dreams visit us night after night, and their true purpose is still uncertain. Sometimes they replay memories, sometimes they weave nonsense. Sometimes they carry vivid scenes that stay with you for years. Do dreams help the brain process emotions, rehearse dangerous situations, or solidify new learning? Are they just side effects of the sleeping brain trying to make sense of its own activity? Different lines of evidence point in different directions. What we know is that dreams can terrify us, comfort us, inspire us, or confuse us, and they vanish too quickly to pin down. Our perception of time stretches and compresses in ways we don't fully understand. A moment of danger can feel slow and thick, as if each fraction of a second expands. A vacation can feel long while you live it, but short in memory, or the opposite. Childhood seems to drift, adulthood races. Maybe our brains judge time by how much information they process. More novelty equals longer subjective time. Maybe emotional intensity changes our internal clock. We can measure brain regions that track time, but the full story of why some hours crawl and others flash past is still incomplete. We don't really know how memories are stored and recalled. We know they're not like video files. Memories are patterns spread across networks of neurons, reconstructed each time you remember them. The hippocampus is crucial for forming and indexing memories, but long-term storage seems distributed. Why do some memories stick for a lifetime while others fade in days? Why can a smell suddenly throw you back decades with shocking clarity? Why do memories sometimes change when we recall them, becoming less accurate while feeling more real? The biology gives hints, but the complete algorithm remains unknown. Our emotions run deep, but their exact origins are debated. Our basic emotions, like fear, joy, anger, and disgust, hardwired, universal patterns built into our brain architecture, or are they constructed by the brain from more general building blocks, bodily sensations, predictions, and cultural meanings? We can point to regions like the amygdala, insula, prefrontal cortex, and chemicals like dopamine and serotonin, but the full map of how raw chemistry transforms into the feeling of heartbreak, of awe, of envy, or of peace is still blurry. Creativity appears suddenly, and no one knows exactly where ideas come from. A problem sits in your mind for days, nothing happens. Then, in the shower or on a walk, the solution appears as if from nowhere. Artists, writers, composers, and scientists often describe their best ideas as arriving unbidden. We see brain networks that seem to correspond to idea generation and idea editing, and we know that rest states and daydreaming matter. Still, there is something about that sudden jump, that leap from chaos to a precise new thought, that defies easy explanation. Deja vu makes the present feel like a memory. You walk into a room you've never seen, yet it feels eerily familiar. You remember what you're about to experience, even though you logically know you can't. Perhaps the brain's memory system misfires, flagging a new moment as familiar by mistake. Perhaps one part of the brain processes the scene slightly before another, creating the illusion of repetition. The experience is intense, vivid, and brief, and its mechanism remains elusive. Placebos can heal in measurable ways, and their power is still mysterious. A person takes a sugar pill, believing it will relieve pain, and the pain lessens. Brain scans show changes that mirror those produced by real drugs. Placebos can affect symptoms of depression, Parkinson's disease, and more. Expectation clearly matters, but how belief turns into biochemical change isn't fully understood. Even more strangely, in some cases, placebos can work even when people know they're taking a placebo. Something in the ritual of care, the meaning of treatment, unlocks hidden healing pathways that science is still learning to map. We don't truly know why we need sleep, only that we fall apart without it. Sleep helps with memory, learning, emotional regulation, immune function, and brain cleanup, but none of those alone feels like the entire reason. Different animals sleep in wildly different ways. Some dolphins let one half of their brain sleep at a time. Some birds nap while flying. Some animals barely sleep at all. Others seem to need enormous amounts. Whatever sleep does, it is so critical that evolution never found a way around it. Aging happens to almost every living thing, yet the fundamental why is still unclear. Cells accumulate damage, telomeres shorten, repair mechanisms falter. But why would evolution leave such vulnerabilities in place, especially when some species seem to escape them? Some theories say Aging is the price of focusing energy on reproduction early in life. Others frame it as a failure of maintenance systems. And then we have oddities like certain jellyfish that can revert to earlier life stages, or naked mole rats that resist many age-related diseases. Aging is deeply woven into our biology, but it isn't as fixed and universal as we once thought. The true limit of the human lifespan is unknown. We know the oldest verified human lived to 122. After about 110, survival curves drop sharply. Is there a hard biological ceiling, or is what we've seen so far just the result of history and chance? As medicine improves, we're pushing average lifespans higher, but the maximum hasn't shifted nearly as much. Could someone live to 150 or 200? Are we bumping up against a wall built into our cells? The boundary between remarkable longevity and impossible dreams is still fuzzy. Some animals can regrow entire body parts, and we don't know why we can't. A salamander can regrow a leg. A starfish can regrow an arm. Some worms can regenerate an entire body from a fragment. When injured, their cells near the wound seem to revert to a flexible, embryonic state and then rebuild missing structures with astonishing precision. Humans share many of the same genes, but for reasons we don't understand, we barely use this trick. If we could unlock it, medicine would change beyond recognition. Others live for centuries with surprising health. Greenland sharks may glide through cold oceans for 400 years. Bowhead whales can live more than 200. Certain clams have been found alive after half a millennium. Their cells manage damage, repair DNA, and resist disease in ways that outperform our biology by a huge margin. Each species seems to follow its own strategy, and we've only begun to decipher them. Some creatures can survive freezing solid. Wood frogs let their bodies fill with ice. Their hearts stop, their blood crystallize. Months later, they thaw and hop away. Certain insects and fish use antifreeze proteins, and tardigrades, tiny water bears, can endure extremes of cold, vacuum, and radiation. We know some of the molecules involved, but not every step of how their tissues endure what should be fatal. If we understood their tricks fully, we might be able to store organs for long periods, or even place humans in some kind of safe hibernation. Whales, despite their vast size and many cells, seem strangely resistant to cancer. This is part of Peto's paradox. Bigger animals with more cells should theoretically develop more cancers, yet whales and elephants don't follow that pattern. Elephants have extra copies of certain tumor suppressor genes. Whales may have enhanced DNA repair mechanisms or other hidden defenses. If we could learn all of their secrets, our approach to cancer could transform. Then there are the mysteries of movement and navigation. Birds can sense Earth's magnetic field, but we don't know exactly how. Tiny songbirds migrate across continents. Arctic terns circle the globe. Even on cloudy days, with no sun or stars visible, they stay on course. Some evidence points to magnetite particles in their bodies. Other clues suggest specialized proteins in their eyes allow them to see magnetic fields as faint visual patterns. The complete mechanism, how the brain translates these signals into a mental map, is still unclear. Birds live in a world where direction is woven into the air itself. We're still trying to read the compass they carry inside. Monarch butterflies migrate with precision across generations. The butterflies that leave North America for Mexico in autumn are not the same ones that return in spring. Several generations pass along the route, Yet each year, the descendants arrive in the same mountain forests, the same clusters of trees. They use the sun, internal clocks, and perhaps magnetic cues, but how the details of this journey are encoded and passed along remains a mystery. Salmon, sea turtles, whales, and many other animals navigate with accuracy that still surprises us. Salmon return to the same rivers where they hatched. Turtles crawl onto the same beaches where they emerged from the sand years before. Whales follow routes across featureless ocean. They use stars, smells, magnetic fields, currents. Yet, the exact navigation software their brains run is beyond our current understanding. Homing pigeons find their way back from almost anywhere. They can be carried hundreds of kilometers away, released under cloudy skies, and still home in on their loft. They seem to use a mixture of sun position, smells, landmarks, and magnetism, but no single explanation accounts for their uncanny accuracy. To a pigeon, the world is layered with invisible signals. To us, their inner compass is still partly hidden. We also don't know how humans first developed language. Our closest relatives can communicate with gestures and calls, but nothing like the layered, abstract, infinite system we call language. At some point, our ancestors crossed a threshold, from simple signals to sentences that can describe imaginary futures, impossible worlds, and subtle emotions. Did language begin with hand gestures, then move to speech? Did musical, rhythmic vocalizations slowly become more structured? The spoken words themselves left no fossils. Only indirect clues remain in our genes, skulls, and tools. Language lets us share our inner worlds, but its own origin is shrouded in prehistory. Laughter is universal and powerful, but its evolutionary roots are uncertain. Babies laugh before they speak. People laugh when they're happy, nervous, surprised, even when they're overwhelmed with sadness. Laughter bonds groups, releases tension, and changes our physiology. It may have evolved as a signal that danger has passed, or as a social glue in playful interactions. But why it feels the way it does, why that particular sound, that particular rhythm, is still somewhat mysterious. Music might be one of the strangest human behaviors of all. Organized sound can make us cry, dance, remember, or feel connected. Every culture has music. It doesn't obviously feed us, shelter us, or directly help survival. Yet, it reaches into the brain and body in deep ways. It can help stroke patients, calm infants, stir crowds. Did music evolve from courtship displays like birdsong, from coordinated work songs, from emotional communication between parents and babies? Or is it a side effect of other abilities that turned out to be incredibly useful? We don't know why melodies and rhythms speak so directly to us, but they do. Love, the force that shapes lives and histories, is not fully understood. We can describe some of the chemistry: dopamine, oxytocin, bonding circuits. We can propose evolutionary reasons for pair bonding and parental care. Yet none of that fully captures why love can be so overwhelming, why it persists in the face of hardship, why people sacrifice so much for it. Love sits at the intersection of biology, memory, story, culture, and something that feels bigger than all of them. Humans cry emotional tears, and we don't really know why. Tears keep our eyes healthy, but emotional tears show up when we're sad, relieved, moved, or laughing too hard. They seem to invite comfort, signal vulnerability, and build bonds. Some studies suggest they may help regulate stress, but why this particular behavior, salty water, spilling from our eyes, became part of our emotional toolkit is still unclear. Across cultures, myths echo one another in curious ways. Flood stories, sky gods, trickster figures, underworld journeys. Similar themes appear in places that never shared direct contact. Maybe there are common patterns in the human mind: fear of death, awe at the sky, longing for rebirth. Maybe stories traveled farther and older than we realize. Maybe the brain comes preloaded with narrative templates that tend to generate similar tales. Whatever the reason, myths feel ancient and strangely familiar, even when they come from worlds very different from our own. Humans often help strangers, and the full origin of this instinct is still debated. We donate to people we'll never meet, rush to help in emergencies, and build systems to protect people outside our families. Some of this can be explained by group selection, reciprocity, and reputation, but humans frequently go beyond calculated benefit. Children help spontaneously, long before they think in terms of getting something back. Somewhere in our evolution, a tendency toward cooperation and compassion took root. We're still piecing together exactly how and why. Civilizations rise and fall, and the deep patterns behind these cycles remain uncertain. From ancient Mesopotamia to Rome to the Maya, powerful societies have flourished and then collapsed. Climate shifts, resource depletion, war, disease, internal corruption all play roles. Some researchers see repeating patterns: growth, complexity, strain, and collapse. Others emphasize unique local stories. We know collapse can be fast and surprising. The exact tipping points are hard to predict. Human societies are as complex as ecosystems, and we're only beginning to understand the forces that shape their lifespans. Human curiosity itself is a mystery. Why do we care about galaxies we'll never visit, particles we'll never touch, histories we'll never live? Survival doesn't require pondering quantum fields or distant exoplanets, and yet, here we are. Curiosity leads us to explore, invent, and imagine. Children ask endless questions long before any of the answers matter for daily life. Maybe curiosity began as a simple survival advantage and then grew far beyond its original purpose. Maybe it's a defining feature of minds like ours, an urge to push beyond the known, even when there's no immediate reward. Storytelling is universal, and we don't know exactly why we need it. Every culture tells stories around fires, on screens, in books, in whispered conversations. We crave narratives with beginnings, middles, and endings. They teach, comfort, warn, entertain, and knit communities together. They let us rehearse danger safely and share emotional experiences with people we've never met. But why are we so hungry for them? Why do imaginary worlds move us so deeply? No other species spins tales as we do. Story may be one of the deepest expressions of what it means to be human, and one of our oldest, most persistent mysteries. Even the sky above our heads holds unsolved puzzles. Ball lightning, glowing orbs of light sometimes appear during storms, and we still don't know exactly what they are. Reports go back centuries, floating spheres drifting through fields, hovering in rooms, sometimes passing through windows and vanishing with a pop. For years, many scientists doubted they existed. Now we have credible observations and a few recordings, but the mechanism remains unclear. Plasma, burning vaporized material, exotic electromagnetic structures. Whatever it is, it's rare, unpredictable, and stubbornly difficult to study. Earthquake lights occasionally flicker in the sky, and their cause remains uncertain. Flashes, glows, and strange luminous phenomena have been reported before, during, or after earthquakes. Some theories point to stressed rocks releasing electrical charges, others suggest atmospheric effects. Not every quake produces them, not every reported light is real, but enough remain that we know something strange is happening at the intersection of geology and the sky, and we don't yet have a complete explanation. Some volcanic eruptions are unimaginably violent, and we can't fully predict which ones will be. Most eruptions are dramatic but limited. Some, however, like historical super eruptions, have changed climate and reshaped life on Earth. Pressure builds underground as magma and gas accumulate, but exactly when and why the balance tips from rumble to catastrophe is hard to know. We measure tremors, gases, and ground swelling, but volcanoes still surprise us. We don't know exactly why Earth has active plate tectonics when other rocky planets don't. Earth's surface is broken into drifting plates that collide, slide, and pull apart, driving earthquakes, mountain building, and volcanoes. This motion helps regulate climate over long time scales, cycling carbon and maintaining conditions where life can thrive. Mars and Venus lack such activity today. Perhaps Earth's abundance of water lubricates the crust. Perhaps its internal heat and composition landed in a narrow range that favors plate motion. Whatever the recipe is, we haven't fully worked it out. The origin of Earth's water is still being argued over. Was most of our water delivered by icy comets and asteroids? Did it outgas from deep within the planet over billions of years? Chemical fingerprints point in different directions. It may be a mix of sources, but the exact proportions remain unknown. Every glass of water you drink carries a history that stretches back to the early solar system, and we haven't yet traced every step. The far side of the moon looks very different from the side we see, and no one is completely sure why. The near side has large, dark volcanic plains. The far side is rougher, more heavily cratered, with hardly any similar maria. Some theories involve differences in crust thickness, heating from Earth's gravity, or ancient impacts. None has perfectly closed the case. The moon always shows us one face, and the other still keeps some of its story to itself. Deep beneath our feet, Earth's core generates a magnetic field we still don't fully understand. Liquid metal swirling around a solid inner core acts like a dynamo, creating a protective magnetic shield that deflects charged particles from space. We know the basics, but we can't observe it directly. Why does the field sometimes weaken? Why has it reversed completely many times in the past, with north and south flipping places? Our models are improving, but the hidden workings of the core remain partly mysterious. Ice ages come and go, and though we understand pieces, the full pattern is still being decoded. Changes in Earth's orbit and tilt alter how sunlight falls on different regions. Greenhouse gases, ocean currents, volcanic eruptions, and feedback loops all play roles. But why ice sheets grow and retreat in exactly the rhythms they do is a complex puzzle. Human-driven climate change now sits on top of these natural cycles, adding a new layer of uncertainty to a system we don't yet completely grasp. Mass extinctions have punctuated Earth's history, and not all their causes are fully settled. Some, like the asteroid that ended the age of dinosaurs, have strong evidence. Others seem to involve overlapping crises, volcanic eruptions, ocean anoxia, climate swings, shifting continents. why some species vanish while others survive, why some collapses are slow and others geologically sudden. These are questions paleontologists are still working through. Even our own solar system is full of unsolved puzzles. Saturn's rings look young, and we don't know exactly how they formed. They're bright, mostly ice, and relatively clean. If they were as old as the planet, they'd likely be darker and more contaminated by dust. Recent measurements suggest they may be only a few 100 million years old, new by cosmic standards. Did a moon get torn apart? Did comets shatter in Saturn's grip? The exact origin and future of the rings, possibly slowly raining into the planet, are still under investigation. Uranus spins almost on its side, and the reason is still debated. Its axis is tilted by about 98 degrees. One pole can spend decades facing the sun, while the other sits in darkness. A massive collision might have knocked it over. Multiple smaller impacts could have done the same, or something in its early interactions with other giant planets could have slowly tipped it. With only one close flyby decades ago, we simply haven't seen enough to be sure. Venus rotates backwards, slowly, and its history remains strange. On Venus, the sun appears to rise in the west and set in the east. One day, there is longer than a year. Was its spin reversed by a huge impact? By tidal interactions with the sun? By internal dynamics coupled to its thick, swirling atmosphere? All of these ideas have strengths and weaknesses. Beneath its clouds of acid and heat, Venus still hides its story. Neptune hosts howling winds and shifting storms we don't fully understand. Far from the sun, where little solar energy arrives, Neptune still stirs with immense weather. Dark storms appear, wander, and vanish. Winds blow faster than any on Earth. Internal heat likely plays a big role, but the exact circulation patterns, energy flows, and triggers for these immense tempests remain uncertain. Jupiter's great red spot has raged for centuries and might someday disappear. It's a gigantic anticyclone, large enough to swallow Earth, and it has been seen for at least 350 years. In recent decades, it's been shrinking. Why did it start? Why did it last this long when Earth's storms fade so quickly? Will it vanish entirely, or is it part of a longer cycle we don't yet recognize? Even a storm can be an unsolved problem. We believe comets come from a vast Oort cloud we've never seen directly. Somewhere far beyond Pluto, trillions of icy bodies may orbit the sun in a distant shell. Occasionally, one is nudged inward and becomes a bright comet in our skies. The distribution, extent, and exact origin of this cloud are still modeled mostly on theory, because the objects themselves are too small and too far to detect with current telescopes. Many moons in our solar system hide oceans beneath their icy crusts, and we don't know what lives there, if anything. Europa, Enceladus, and others may have more liquid water than all of Earth's oceans combined, sealed under ice and warmed by tidal flexing. On Earth, life thrives around hydrothermal vents without sunlight. Could something similar exist in those dark alien oceans? We see hints, plumes, chemistry, heat, but no direct proof of life, not yet. Enceladus, in particular, sprays its secrets into space. Geysers near its south pole send plumes of water vapor and ice into space, which spacecraft have sampled. They contain salts, organics, and signs of energy sources that on Earth would be promising for life. But what exactly is happening at the seafloor of that hidden ocean? Are there hydrothermal vents, complex chemistry, anything alive? We don't know. Titan, another moon of Saturn, has rivers and seas of methane, and something is constantly replenishing them. Sunlight should slowly break methane apart in Titan's atmosphere. Over time, the lakes and seas should vanish, but they remain. Perhaps cryovolcanoes erupt, releasing fresh methane from the interior. Perhaps exotic chemistry is at work. Some have even speculated about strange methane-based life, though there's no evidence yet. Titan's weather cycle mirrors Earth's water cycle in eerie ways, but with a different liquid entirely. Mars once had flowing rivers and maybe lakes or oceans. Where did the water go? We see dried up river valleys, deltas, and mineral deposits that form in water. Today, most of Mars is cold and dry, with only ice at the poles and permafrost underground. Some water escaped into space when Mars lost its magnetic field and atmosphere. Some remains locked in rocks and ice. The details of when and how the planet transformed from wetter to arid are still being pieced together, and along with them, the question of whether life ever emerged there. Finally, we arrive at some of the deepest questions of all: the nature of reality itself. Mathematics, a creation of human minds, somehow describes the universe with uncanny accuracy. Equations invented for curiosity later turn out to govern electricity, gravity, or quantum particles. Mathematical structures dreamed up on paper show up in the behavior of real things. Is math discovered or invented? Why should abstract symbols and patterns match the workings of the physical world so closely? We don't have a satisfying answer. The unreasonable effectiveness of mathematics is itself a mystery. The constants of nature have specific values we can measure but not explain. The speed of light, the charge of the electron, the strength of gravity, all are numbers that could, in theory, have been different. Change them slightly, and stars might not shine, atoms might not form, chemistry might fail. Why these values and not others? Maybe they're accidents. Maybe they're selected by deeper laws we haven't found. Maybe only universes with certain combinations produce observers, and so, of course, we find ourselves in one of those. The cosmic dials are set, but we don't know who or what set them or why. We don't know whether true randomness really exists. Quantum events seem intrinsically random. No hidden pattern, no deeper cause, just probabilities. Throwing dice or shuffling cards feels random, but is, in principle, predictable if you knew every detail. Quantum randomness might be different, fundamental, irreducible, or there might still be hidden variables waiting to be uncovered. If true randomness exists at the root of reality, then uncertainty is not just ignorance. It is part of what the world is. Time itself remains one of the greatest puzzles in science. Is time a fundamental feature of the universe or an emergent property of deeper structures? Why does the past feel fixed and the future open? Are all moments equally real, like pages in a book, or is the present special? Experiments show that time is intertwined with the space, bending and stretching with speed and gravity. Yet, our inner experience of time, to be here now, is something no equation has fully captured. When the universe formed, matter somehow won over antimatter, and we don't know exactly how. The Big Bang should have created matter and antimatter in equal amounts. When they meet, they annihilate into energy. If everything had been perfectly symmetric, there would be almost nothing left. No stars, no planets, no people. Yet clearly matter won the cosmic coin toss. We've observed small asymmetries in how matter and antimatter behave, but they don't seem big enough to explain the entire imbalance. Somewhere in the physics of the early universe, something tilted the scales. Particles have mass because of the Higgs field, but the deeper why is still open. The discovery of the Higgs boson confirmed that an invisible field permeates space. Particles interacting with this field acquire mass, like swimmers feeling resistance in water. But why does the Higgs field have the strength it does? Why do different particles couple to it so differently, giving us the zoo of masses we see? The mechanism is known. The reasons behind its specific details are still a mystery. We don't know if reality is continuous or fundamentally pixelated. To our senses, space and time seem smooth, but many theories of quantum gravity propose that at an unimaginably small scale, the Planck scale, space and time come in discrete chunks, like pixels on a screen. No experiment has reached those scales yet. If space-time is granular, the rules of physics might change in subtle ways. If it's continuous all the way down, we must explain how infinities are avoided. Either answer will reshape our understanding of what space and time truly are. We suspect there may be a smallest possible length, but we haven't found it. The idea of a minimum length helps reconcile quantum mechanics and gravity. Below that scale, distance might lose its meaning. But directly probing such a scale would require energies far beyond anything we can generate. For now, the smallest bricks of reality, if they exist, are hidden behind a wall we cannot cross. And overarching it all is this: the laws of physics could have been different, and we don't know why they are what they are. Why this mix of forces, particles, and rules? Why a universe where complexity, life, and consciousness can arise at all? We can describe the laws with stunning precision. We just can't yet explain why these laws, and not others, are written into the fabric of reality. You've just drifted through 100 mysteries that stretch from the first instant of the universe to the deepest corners of your own mind. We've touched questions about time and space, life and death, love and laughter, stars and storms, oceans hidden under ice, and songs hidden in hearts. For every answer science has found, there are more questions waiting in the dark. Some of these mysteries may be solved in your lifetime. Others may take centuries. Some may never be fully explained, but that isn't a failure. It's part of the wonder. To live in a universe with so much still unknown is to live in a universe rich with possibility. As you lie here now, feel how gently these questions can hold you. You don't need to resolve any of them tonight. You don't need to remember every detail. Let them drift around you like distant constellations, bright points of curiosity in a soft, dark sky. Each one is an open door, but you don't need to step through. It's enough just to know they're there. Let your breathing settle into a slow, easy rhythm. Feel your body grow heavier, supported completely. Imagine yourself floating among these mysteries, moving past galaxies of questions, seas of unsolved puzzles, islands of wonder, always safe, always at the quiet center of it all. The universe may never run out of mysteries, and our curiosity, that small flame inside you, may never go out either. But for now, it can dim just a little so you can rest. If you happen to still be awake later, you're always welcome to come back for more sleepy science facts and wander again through the unknown. For tonight, though, There are no answers to chase, only the soft comfort that mystery itself can be a lullaby. Good night. May your dreams be filled with wonder and love.